All righty. So let's see where we were talking about. Uh, all right. Well, let's back up a little bit. Okay, so we had talked about why we need renewables, and the basic idea here is that if you look at the IEA's net zero scenario that they published a couple of years ago now, I tried to look for an update, but this still appears to be the state of the art. There is a variety of different things that are going to change CO2 emissions going through 2030. There's going to be some increases due to just increases in human activity and that sort of thing, but a lot of reductions that can be made. And a big part of those reductions are going to come from the use of renewable energy rather than fossil fuel-based energy. So you can see that they're a substantial part of the solution. They're not the only solution, but they are in there. And if we look at their projections about where the energy supply is going to go through 2050, you can see that wind, solar, and other renewables up here are going to make up more than a third of energy generation by 2050 in their net zero scenario. So we're still going to be using, by their projection, oil and gas and coal, but a lot of our energy is going to be coming from renewables. Okay. And I just want to, I showed this slide like the first day of class, I think, or maybe the second day of class, but when you look at other people's projections of energy use by 2050, you can see again that the EIA annual energy outlook from last year, a lot of their scenarios, basically you've got about a third-ish, a quarter to a third of generation from renewables. And in BP's energy outlook from this year, under their net zero scenario, again, by 2050, they're saying more than half renewables to reach net zero. So a lot of projections, and so basically they're a big part of what we need to get to net zero carbon emissions. Renewables also, excuse me, have a couple of other advantages. One of which is that they provide better energy security. So I think I made this point last week, which is that a lot more countries have renewable energy resources than have substantial fossil fuel resources. And so a good example of this is if you look at the European Union in general, obviously Norway, the Netherlands, and the UK have substantial offshore oil and gas deposits. However, a lot of the countries in the European Union do not. But what they do have is wind and solar potential because the sun is there and it's windy. And so, in fact, let's see, this is renewable generation growth from 2021 to 2023. And what you can see is that the growth there in renewable energy has been able to supplant a lot of the loss of gas that would have been coming from Russia to generate electricity in the EU. So again, this is a way of insulating yourself from some of these geopolitical problems that arise when you're relying on other countries to supply your energy. And then I just got to throw this in there. Of course, we know that renewables use a lot more of these critical minerals than fossil fuels. So there is a little bit of an issue there that you have to think about. But overall, it's cheaper also, in addition to insulating you from the geopolitical stuff. So this is an interesting plot. This is looking at levelized cost of energy, and this is per megawatt hour. And it's just looking at how the price of these things has changed, going back to the late 2000s up through 2020. And one thing you'll notice is that by 2020, coal and, which is right there, and then certain types of gas generation are substantially more expensive per megawatt hour than wind and solar. So natural gas is pretty competitive, but some of these other ones are more expensive. So it also gives you access to cheaper energy. In case you're wondering, peaker plant, these are gas-powered gas turbine plants that are only turned on when there's a large spike in demand. And so the reason that they're so expensive is because they're very inefficient, because it takes them a while to heat up and come to full operating capacity. And during that time, they're not operating as efficiently, so you're kind of wasting a lot of gas. So that's why these peaker plants are so much more expensive. Here's another plot that basically shows the same thing. So when you look at certain types of renewable energy generation, I'm going to look specifically at utility scale solar and wind over here. So when you compare those, let's see, these are cost, again, levelized cost per megawatt hour. You can see that these ones, and even geothermal, if you want to throw that in there, are cheaper on average than coal, gas peaker plants, and even nuclear to some degree, and even cheaper than the gas combined cycle estimates. So again, just to make that point, the renewables are good because they insulate you from geopolitical stuff. They are inexpensive. They are obviously low carbon. The problem, though, is that they're intermittent. Okay, so the sun doesn't always shine, the wind doesn't always blow. Here's a plot of, this is some random day in November 2 years ago. This is wind and solar generation on the ERCOT grid. You can see, obviously, the solar generation picks up when the sun comes up, and then it goes down when the sun goes down. And then there are diurnal cycles to wind also that we typically see. Another example would be tidal energy. Okay, tides come in and go out regularly, but there are times when you can't extract any energy from them, like during your ebb tide phase. So you have to deal with that if you're integrating renewables onto your electric grid. And the best way to do this is to have some type of energy storage, so that when you have excess generation, you can store that energy. And then when you have excess demand, you can discharge the energy that's been stored. And so there's a number of different storage technologies, including mechanical techniques. So we had a good presentation on gravity storage, right? But there's other types of mechanical ones, including pumped hydro, flywheels, that sort of thing. There's capacitors and batteries that can store as electrical or electrochemical energy. And then there's also thermal storage in terms of ice, or you can use hot rocks to store heat. And then hydrogen is a chemical type of storage. So all these different types of storage can be integrated together to give you grid reliability if you have a lot of renewables on your grids. And so, utility scale energy storage, has a lot of different applications that you can use in terms of, grid stabilization. There's also a kind of financial component, which is if you're operating an energy storage facility, you need to be able to purchase the energy cheaply, and then when you discharge it, you need to be able to make a profit. So there's kind of the arbitrage component to that. And then there's a bunch of other stuff. So it's not as simple as just saying, okay, let's throw a bunch of batteries on the grid. You have to think carefully about what you're actually trying to do with that energy storage to make the grid overall more reliable. Okay, so the big issue that we currently are dealing with integrating storage onto electric grid is the time scale of the storage and the discharge cycles. So a lot of, specifically here in Texas, a lot of battery storage has come online over the past year and a half, and a lot of them are using either lithium ion or lead acid batteries. And the problem with those is that they're really good at storing the energy, but they will discharge over a time scale of minutes to maybe, an hour or two. And so if you think about something like the power outages that we've experienced over the past few years, those last for days. And you're not going to be able to make up for that with the current battery storage we have. These are really only good for, balancing the grid during times of peak demand. So like 5 to 6 p.m. on a hot day in August, these batteries are awesome. Okay, they kick on, they provide a little bit of extra juice, but that's really all that they're good for at this point. If you want much longer term discharge of your stored energy, you need to look at things like pumped hydro, hydrogen, compressed air, things like that. That's really where it's at. And so, thinking specifically here about Texas, we don't have a lot of pumped hydropower here because, it's especially in Western Texas, it's fairly dry. There's not a lot of water. And so, you might think about maybe hydrogen might be a big part of our grid in the future. So something to think about. Okay. So if we think about at the scale of a typical US household, let's see, your power rating is on the order of a few kilowatts, right? Where this number has come up before. And so, these kind of household scale energy storage is becoming very popular. Tesla offers their Powerwall system, which can be integrated with rooftop solar array. Those are pretty cool. Another thing I just read the other day about a company based out of Dallas that's going to start offering battery storage to houses where it's basically just pulling electricity off the grid when it's cheap, and then it stores it. And then you can use it for times, if your power goes out or, if there's a conservation appeal or something like that. So that's kind of that end of things. On the other side, the Austin Energy, which is our local electric utility here in Austin, in 2019, the usage was gigawatt scale. And so if you want to start having real utility scale energy storage, you need to look at some of these larger scale type systems. Okay, so a couple of slides here looking at, in the United States, what are the types of energy storage that we currently have? So this is a nice, from a website that's operated by Sandia National Labs, looking at energy storage installations by year. You can see that it's dominated by this kind of maroon color, or burnt orange, I guess, which is pumped hydro. So pumped hydro is the dominant type of energy storage in the US. If we remove that and look at the runners up, it's really dominated by lithium ion battery and then sensible heat. So this is thermal storage and then battery storage. So that's a lot. And you can see, particularly within the past 6 or 7 years, there's been a lot of battery storage coming on the grid. And that's been driven by advances in efficiency of lithium ion batteries. So good stuff to look at. If you're interested, in the interest of time, I'm not going to go to this website, but you can go to this website and poke around. There's some pretty cool stuff on it. Okay, pumped hydro, we'll talk about that for a minute. It's a pretty straightforward process that you have an upper reservoir and a lower reservoir. When you have excess energy, you pump the water to the upper reservoir. When you need the energy, you run it back down to the lower reservoir. And there's a turbine here that generates electricity. The largest pumped storage is in Virginia. It's in the Appalachians there, at Bath County Pumped Hydro Station. Generates 3 gigawatts. That's the largest one in the US. We had a news item, I think last week, about a much larger system in China, which I think they were targeting hundreds of gigawatts. So that's pretty big. But that's typically what we have. The elevation difference is about 1,000 feet or 1,300 feet between their upper and lower reservoirs, which you can see here. Let's see. I'm going to skip over some of the technical details because I want to get to microgrids. Yeah, compressed air is another way of doing storage. There's a big facility in Alabama that's rated to almost 3 gigawatt hours. Something about the thermodynamics, which I'm going to skip over. Okay. Battery storage, like I said, we have a lot of battery storage in Texas. One particular large-scale system is out in the town of No Trees. Who's been to No Trees? Been to No Trees. It's west of Odessa, and I used to drive through there a lot when I worked out there, going to and from the oil fields out in Loving County. Anyway, here's a picture of No Trees. There are trees there. But yeah, this is where it's located. It's out here. That's Odessa. So out here, kind of middle of nowhere. But they've got a big battery storage project that's integrated with wind generation. So that's a good way of using that excess wind energy. Okay, they use lithium-ion batteries. Let's see a little bit on the costs associated with this. Lithium-ion is, still relatively cheap. But compressed air and is actually, for the duration of storage, is actually the cheapest right now. So I wonder if we'll see more of that in the future. Okay. So let's see, blah, blah, blah. Yeah. So we can put all of this together in something called a microgrid. So a microgrid is an integrated system of generation, distribution, end users, and storage. And this is a good way of thinking about how you can put everything together to give you reliable electricity generation. Okay, and per NREL, who sets the definitions of these things, you need to have generation, consumption, and storage locally, and then there's usually a connection to the main grid. And I think I've asked you this trivia question before, but the largest microgrid in the US is right here at the University of Texas at Austin. It's a pretty cool system, actually. We've got local electricity generation right across the street here, where we generate hot water, and we use some of that to, distribute to campus for district heating and cooling. We have thermal energy storage in these giant drums of cold water, which I'll show you in a little bit. And then there's, also steam generation that can be used for heat exchange and that sort of thing. So the way the power plant works is that we've got, because it's combined district heat, you can recycle some of the waste heat to produce hot water, which then can be circulated around campus. And so that really increases the efficiency of your system, where you're only losing about 20% to waste heat. So that's how the power plant works. I mentioned the thermal storage. You may have noticed next to the San Jacinto garage, this big thing. It's a big tank of cold water. That's thermal energy storage. And we use that, when they have excess generation, they cool down the water, they store it there, and then in the summer, when we need it for cooling, we can extract that hot water. There's another one at Red River and MLK that looks like that. So that's what those are. Let's see, CO2 emissions have been declining over the past couple of decades because they've been doing a really good job with that. Austin Energy also operates some district systems with these ice generating plants that McKinley talked about earlier. And there's several of them around town, which again, you wouldn't know it, but they're on the tops of like parking garages and stuff. So they just make ice at night and use that to circulate cold water. They have a district cooling system downtown. They have another one up in the Domain. So they're really working on it. Okay. So that was a little bit of a rushed, disorganized end to our semester here, but I appreciate you all being in the class. You've all done a fantastic job. I hope you've learned something and it's been fun. And I'm looking forward to reading your final reports. So thank you all.